Hello there everyone. In this video we're going to go through one of the documented examples in the Ciw Python package on the subject of how to simulate reneging customers. We're just going to read through the documentation together today. So Ciw allows customers to renege, that is leave a queue after a certain amount of time waiting for service. At least that's how we usually like to formulate and simulate that, is to think that after some amount of time they renege, but you could have other kinds of rules. While it will eventually mean that if they renege after some amount of time, the time can actually be reformulated as an implicit thing, but Ciw and many other formulations make time an explicit factor for when reneging happens, for if it happens, is after some amount of time. So in Ciw, this works by sampling from a reneging time distribution. That's a Python variable name for an argument, a parameter, giving the date that a customer will renege if their service is not started by that time. It doesn't have to be finished by that time, but it has to be started. For example, let's say that we have an MM1 queue. If you don't remember, that means that the inter-arrival times of new demand on the service or the queue is exponentially distributed, but otherwise the mean inter-arrival time is constant. And the same thing for the service time, which is what the second M stands for, and that last slash number 1 means one server. So here they've decided for the arrival rate, conventionally denoted lambda, that it's 5, and the service rate is 2. So correspondingly, their averages are the reciprocals of these in the long term. Ciw, where customers renege if they have spent more than 6 units of time in the queue. Okay, great. So let's make this renege customer, I guess. Sure. And let's import the Ciw Python package, as we always have to do when we're working with Ciw. And let's define a network variable, and following along with what they've got there, we'll have create network. And we need to define the arrivals. This is a required field, and we'll follow their example of saying that it's just exponential with a rate parameter of 5. And then we can also need to have a service distribution, and here we'll match their service time of 2. Now there's actually a point to this example, right? If we're looking at the reneging time being some amount of time for which if they wait that long, then they leave, that is going to be indirectly related to the service versus arrival times. That if the service time is very strongly dominating very small compared to the arrival times, or correspondingly, and I should say inter-arrival times, or correspondingly, if we say this in terms of rates, if the arrival rate is small compared to the service rate, then often or more often they will not renege when they're waiting, if they even have to wait at all, compared to in this situation, in this example, where the arrival rate is greater than the service rate, meaning that there will be a tendency for the waiting times to get longer and longer, and that correspondingly we're going to have more reneging. Not that the reneging will necessarily balance it all out. I would kind of doubt in a specific example like this that it will, but that's why they've set the rates this way. We actually want to show in this example that the waiting customers are going to end up reneging after some amount of time. So number of servers, in this case 1, just to match the MM1 that we had been given above. And here we're going to fill in reneging distributions, which again, like other fields, if you need a refresher on Ciw, this needs to match the same length as the number of queues or be empty. So deterministic 6. Deterministic here is just to say maybe degenerate is a better statistics term, or even constant. That just means it's going to be that the reneging time is strictly just 6. You can actually have random amounts of time that for each customer when they arrive, a reneging time is chosen according to this distribution, and it could be exponential, it could be gamma, it could be a variety of different probability distributions. That's all fine. So that's our queuing network. Now let's set up queue.seed, and here we're just going to use a seed of 0. Why not? Because we don't we want to reproduce roughly what they're doing for the sake of example. So we'll define a simulation class instance, and we'll pass in network. And I think that they're doing this mostly to prevent a numerical issue that could have come up in this example when they made this example. But we're going to set exact, and that means using decimals behind the scenes, so not just floating point numbers. And that's to help prevent some numerical issues, I expect. So we'll actually run the simulation, simulate until a maximum amount of time of 10 units of time has elapsed. And let's say that after that, we're going to grab all of the records. So if you're not familiar with this aspect of Ciw, Ciw will collect up records for you of the basically where the customers, as they call it in this software, show up and leave. The events, basically an event log of what happens to the customers. Okay, so we'll get all of them, all records, that's fine. And they wanted to show the maximum waiting time. And this kind of makes sense, like it should be strictly less than 6, and I think that's maybe where they're using the decimal type or the exact argument that we passed in for 5 decimals, so that we can see that the maximum of the waiting times has to be strictly less than the reneging time, otherwise they would have reneged. So max wait time, write it out this way as a list comprehension, and we'll say record dot waiting time for record in records if record dot record type is equal to comparator equal, not assignment, service. That is, they actually got a service, right? They didn't leave the simulation for some other reason. They actually got served. Okay, so we'll take a look at that value in a little bit. Oh, we actually need to compute the maximum. Let's do that. And let's also, not the cleanest thing, I should turn my formatter back on, but I'm not going to do that in this video. Okay. So then let's also, for the basis of comparison to that, look at what the values are for the waiting times if they reneged. They should all be exactly 6, and we should think that they're exactly 6 because 6 is kind of the only option for the ones that reneged. Because we chose a deterministic distribution, that is to say you can't make this simple comparison that we're going to make in general. It holds because of the special assumptions we made for this example. So we'll grab record waiting time for record in records if record dot record type is equal in value to renege. So what should we do to compare? What we're supposed to see from their example is that they're all the same. And we're not simulating for a very long time, so maybe we'll just print that. Sorry about the notation, is a little bit messy here, but I just don't feel like fixing it right now. Okay, so we have a couple of print statements because we're going to run this from the command line. Reneging customer, and there's our 5.8880, 5.8880, and these are all 6.0000. And likewise, that's what that is there. So we've reproduced the example. Hopefully every time we see one of these in our videos on the Ciw Python package, that you'll get some sense of also defining simulations in Ciw is pretty straightforward, at least for the cases that it supports. Now, by default, when a customer reneges, they leave the network. That is, they are sent to the exit node in terms of the underlying implementation. So every Ciw simulation network will have an exit node, and it's just a catch-all for anything that leaves will be stored there. So it doesn't actually delete them during the simulation. That's something to keep in mind in terms of the scalability of this software. So let's take a note. Similarly to all other customer level keyword arguments, reneging time distributions can take either a list of distributions indicating which reneging distribution is used at each node of the network, or a dictionary mapping customer classes to each of these lists, allowing for different reneging times for each of the different customers. Which makes sense if you want to model something like, let's say, diseases, and that we're talking about maybe that after some amount of time, they become either too sick to be able to make good use of that service, or that they'll even, I guess, as a special case of that, they may even pass away or die from the disease. So it's a kind of competing event that happens with reneging. They either get served or they get reneged. One of them will happen before the other. And they say by default when a customer reneges, then they'll leave the network. But actually, and that's correct, but if I recall correctly, there are ways of using Ciw where they actually go somewhere else. But there are custom classes that I think Ciw now supports in its API where you can specify exactly what those rules are. Okay, that's enough for this video. That is how to simulate reneging customers, at least in a simple case, and I'll catch you next time.